Our next talk is by Erwin Bolthausen from Zürich on the two-dimensional random walk in isotropic random environment. You see, we have a very flexible title of the conference, Random and Ergodic Operators. And believe me, there are random operators there, even if you don't quite see them. But in this particular case, they are there. So not all the talks will be exactly about the spectral theory. This one is, but not unrelated. If you can listen carefully. Go ahead.
Ilya, I suspect you prepared the audience to your own talk.
Yes, true. By the way.
Okay.
I had my doubts first, but now you convinced me.
Okay, so thank you very much for the invitation to talk here. And actually, I have to apologize for two things. First of all, as Ilya said, that it doesn't fit to really ergodic systems, and secondly, that it is actually not the final result. It's just it's a problem we are working on since a couple of years actually, with Oversight Uni and also with a former PhD student, Erich Bauer. And over the years we have made some progress of understanding it, and also on a technical level, but I will mainly talk about the principal framework and what we think is a picture in these two-dimensional random walks in random environments. Now, just it's a standard model of a random walk in random environment on the d-dimensional lattice. Now, forget for a second the random environment. It's just a Markov chain, say in a disordered. With the disordered transition probabilities, if you want in a disordered environment, which in principle could be also non-random, but in a second it will be random. So the disorder is given by just a field of random transition probabilities. Okay, I write it as elements of this space of omega, which is just given by, what you're taking is you're taking the probability distribution on the nearest neighbors of 0, say on the lattice, just so in dimension 2 it would be just 4 elements. So this P is just the set of probability distributions on these 4 points, and then our basic probabilities or the basic space is just you take the infinite product of this space. So essentially that means that every omega attaches to every point x transition probabilities here. So then for it's described here for a fixed environment, and if you have to fix a starting point. Typically it will be 0. So you're looking just at the Markov chain with what people call quenched law, namely it depends on this omega. You start in x, and the transition, the probabilities with which you jump from y to y plus e, you can just jump to the nearest neighbor. Is just given by these omegas here. So that's the Markov chain with this fixed with this disorder. Now the next point is, of course, I'm assuming this environment or this disorder to be random, and actually it is random in a very simple way, namely just as a product measure. So you are just fixing probability distribution on this set P. So in the two-dimensional case it would just be on this set of probability distributions on 4 points, on the 4 neighbors, and then we are just taking an infinite product measure here. So then we also have always a small disorder assumption. Actually there are no results in higher dimensions except in some special cases. So without a small disorder assumption, because all methods up to now are essentially perturbative. So you see, if you would just jump by a symmetric random walk to the nearest neighbor, of course you would jump with probability 1 divided by 2d, and we assume that that's not the only possibility we could take, but that's maybe the most stringent restriction, namely that all the transition probabilities are within a parameter, small parameter delta, close to this symmetric random walk case here. Now, okay, okay, we have one result where we drop this assumption here. We have this isotropy assumption, namely that mu is invariant under lattice isometry, under reflections and rotations on the lattice. So that's most of the results in higher dimensions assume this invariance property here. Now, just as an example, so a simple example actually which is one of the most difficult ones, and actually the one we want to solve. So, and we don't have a final result. So, you take the two-dimensional lattice, and then you can choose. So with probability 1/4 that this is your random environment. With probability 1/4, you choose one of the four possible directions.
Can you draw a picture on this?
Oh, okay. So you have at the point x, you choose a preferred direction, which I called E hat. Which I choose with probability 1/4. So for every possibility, for the four possibility, and then in this direction I jump with probability 1/4 plus epsilon, and in the other ones I jump with say okay probability.
Local drift.
You have just a local drift. So you have 1/4 minus epsilon thirds also in order to get a transition probability. Is the model clear?
Just the isotropy condition, right? This is not on mu, it's on p, right? It's on the global measure for all the other.
It's on the mu. So the mu is you see it just means in this case it just means you choose with probability 1/4 all possible directions.
So it's not on actually. Okay.
Yeah, it's not the p or isotropic. That's of course the whole difficulty.
But you're not. It's not the lattice isometries. It's actually action on p round, right? Because mu is a measure on p round. So this is action on the lattice.
Sure.
Because you could replace the first assumption, right, to be a product measure by some measure p, which can be invariant under lattice.
Yeah, you see, actually that could be relaxed. So for instance, you have finite range or decaying correlations or things like that. So that shouldn't be very difficult. Yeah.
So there's no connection between probabilities on one edge and on its reverse. Is that right? Those are completely independent.
No, at different points x, they are independent. You choose the environment independently. But just think of, okay, to have a simple model, just think you are flipping a coin with four sides, or you just flip a coin with twice. This gives you, this determines the preferred direction. So, and in this preferred direction, you're choosing, you're jumping afterwards with this probability 1 plus epsilon. And in the others, you are jumping with probability 1/4 minus epsilon third. So, is it clear? Is the model clear? So, to everybody. Okay, just to give some reference. So actually, this model has been investigated much. So in one dimension, in quasi one dimensional. So also with together with Ilya and Ilya with other people. Now in higher dimensions, okay, there have been a lot of work by Alain Snitman under some ballisticity conditions. So this means conditions for which you have a law of large number with a limit which is non-zero. Now this is not satisfied under these isotropic conditions. So then you have to have a global preference in one direction here. So now in the one-dimensional case, okay, in this if you have this isotropic condition here, okay, there are these classical results by Solomon and Sinai. So in that case you have a subdiffusive behavior. So that's this celebrated work by Sinai that actually the deviation is only of order. So the typical deviations of this random walk in random environment is only of order log n2 square here. So now the two-dimensional case, okay, I would call it the difficult case. I will explain why it is the difficult case. So and then the higher dimensional case, it's also not okay. It's also difficult, but I would say less difficult than the two-dimensional case. So the dimension 2 is the critical dimension. So in the same sense as 4-dimension is the critical dimension for the easy model or for the standard self-avoiding walk. So now there is a celebrated work by Brigmont Coupian, which is extremely complicated, who proved central limit theorem that you have an ordinary diffusive behavior in dimension 3 and larger. And then there were further works by Snitman-Saitouni in 2007 who treated the continuous time case and space case. And then I had a paper with Saitouni where we looked at exit distributions from large sets and proved that the exit distributions from large sets are essentially the same as those for ordinary random walk. One has to be a little bit careful with the formulations, but that's essentially the point. So in 3 dimensions, at least if you start with small disorders, then we prove that exit distributions from large sets are essentially not different from exit distributions from ordinary random walks. Now, I also had a work with a PhD student, Erich Bauer, where we dropped this isotropic condition to some extent. So I will not go into that, because I want to focus more on the difficulties with the 2-dimensional case. So that's about that's not a complete list of the literature, but some of the key results. Now, the main point, the main tool we are using, and essentially everybody is using, is a kind of perturbation expansion. So up to now, for this type of models, so the only results in high dimensions are in the perturbative regime. So you're using the perturbative expansion, and that is particularly easy and particularly nice if you're looking at these exit distributions. So we are taking, say, a ball of radius L. So we took an Euclidean. Actually, you can take other sets, so it doesn't matter very much. But for the induction step, it was convenient just to work with these Euclidean balls. But you're on the lattice. Then you have a little bit of difficulties because the Euclidean balls are not fitting so well with the lattice situation. But we found that this is still the most convenient setup. And then that's the boundary I'm taking, and then I'm looking at the exit time from this ball. So I'm just looking at this ball. So that's VL, and you're starting somewhere. Typically we start in the middle, but you could also start somewhere else, and then you're letting the random walk run up till it exits. And this gives a probability distribution. So for fixed omega, for fixed random environment, you are getting an exit distribution. But this exit distribution is, of course, a probability distribution, but it depends on omega. So it's a random probability distribution on the boundary. Now, that you can represent by this expansion here. Which is the convergence of this expansion is no problem if you are in a finite box. So I'm looking at this exit distribution. So I'm looking if you're starting at X, that you exit at Z. So now I'm comparing that. The first the 0th term is the one which is just from ordinary random walk. So with small pi L, I just take the ordinary random walk exit distribution here. And then the next term in the expansion is just given by this, I'm multiplying GL with this delta, and then again with this pi. Now, I regard that as matrices, and it's just a product, what I'm having here is just a product of matrices. Now, the GL is just the Green's function of corresponding to this discrete Laplacian, to the ordinary random walk. So probabilistically, it just counts the expected number of visits at the point Z. Where do I have it? Here. So it's just the expected number of visits at the point Z by the ordinary random walk. So that's just the Green's function. But of course, analytically, it's just the Green's function corresponding to this discrete Laplacian. So that's that. Now the pi L I have said before, that's just the exit distribution of the ordinary random walk. And this delta is just then the difference of these transition probabilities. So one-step transition probabilities first coming from the random walk in random environment to the one of the symmetric one here. So you see, so what you are getting, that's an easy computation, that you are getting this expansion. So in first order you get G and then this delta, and then you go with the exit distribution for ordinary random walk. Then the next is G delta, and then pi, etc. You go on in this way. Yeah, so in this way, you're getting this expansion. As remarked, okay, if you are in a finite box, the convergence of this expansion is no problem. So now an important point about this is totally trivial. But is that of course the summation over y of this delta, because all these things are, you see, you're always in the regime where you have transition probabilities. So the difference of transition probabilities, if you are summing, it's 0, because that's clear. So if you're taking here this matrix product of delta with any kernel k, then you can always subtract here, say this k here at the point x, because that's of course, you see it's trivial. So in this way you're getting a derivative, so you're gaining a derivative. This is important, so that's the reason actually that 2 is the critical dimension and not 4. So because you are getting this, you're gaining this derivative. So this means that in later, okay, you will see that later. So in the later point, you are always gaining a derivative of the Green's function, and therefore the critical dimension. You see, for self-avoiding walk, 4 is the critical dimension because in the dimension 4, the so-called bubble diagram is starting to diverge, and in dimension 5 the bubble diagram is converging. But here you're gaining 2 derivatives because of this trivial fact. Sorry, two dimensions because of this fact here. So, okay, we will come to that. Now the first thing is okay. We are looking at the behavior just on the first order perturbation. So I'm just looking at what is happening if I'm dropping everything else and just look at that here. So at this first order perturbation. Now, okay, maybe the simplest thing is I'm just looking at the expectation. So I'm just looking at the expectation under the exit distribution here. Now, of course, if I'm just making one step, so I'm just computing the expectation of this one step, so under the random environment. So that I call psi omega. So that's of course just omega naught at e multiplied by e and summed over e. So that in 2 dimensions is just this sum over 4 terms here. So but that's a random variable. So because it depends on of course on this omega. Yeah, and then from this isotropic condition, of course, I'm having that the expectation. If I'm taking now the expectation under this randomness from the random environment, I'm of course getting 0, and the covariance is just a multiple of the identity. So this is just coming from this isotropic condition here. So because if I'm rotating it, you're getting the same. So you're just getting that the expectation of this so-called quenched expectation is 0, and the covariance is just a multiple of the identity. And because I have this small disorder assumption, of course, the identity is given by a small parameter here. So. Now, what I want to do is, of course, now one of the key problems would be to look at later scales. So I'm taking a small box, so of size L. And then I'm again computing here just okay, this is random walk looked at when it exits from this large ball, and I'm computing the quenched expectation of that. That's of course a well-defined object, but because I want to compare it with original expectation, I just scale it down by L. And then, okay, again by isotropy, I have the expectation 0, and the covariance is again a multiple of the identity. This is just coming from this isotropic condition here. And the question is, how does that compare with epsilon here? So you start with a small, okay, with small variances, with a small covariance matrix, and then you are looking at bigger scale, and you want to know now what can you say about this quantity here? So. Is it somehow increasing epsilon? Then you would say, okay, the disorder is very relevant. So if L gets large, for instance, you start with small epsilon. Is it true that epsilon L gets large, or does it go to 0, or maybe it stays stable? So that's a question. So that's the main question we are trying to address in the 2-dimensional case. Now. okay, if you compute here now this expectation here, I'm always having this 1 divided by L in front because I'm scaling it down. So what you're getting is in the first order expansion, you of course just get that. So you remember this pi L1 was just, maybe I show it again. So this was just this part here. So the first term in the perturbation expansion here. So for this exit distribution here. So you're just getting that and then call psi L1. Of course, the zeroth term coming from ordinary random walk is 0 because from ordinary random walk you're getting 0 expectation here. So the zeroth term is 0. So John.
Sorry, running a little bit ahead of my comprehension here. I just wanted to firm up what we're talking about. This capital X tau L. That's a.
That's just with X. I had that's just a random walk. X is just a random walk.
X is a vector, right?
Yeah, X is a vector. Yeah.
Okay.
So the psi is also a vector here. So it's in the two-dimensional case it is a two-dimensional vector. So it's just a two-dimensional expectation. So and then I look at the covariance matrix, but the covariances between the different components are 0 because of this isotropy. So the covariance matrix is just a multiple of the identity of that.
Okay, so of the 2 by 2 identity matrix.
Yeah. Now this is of course you see this is a random object. This can go to the right or the left depending on omega. So you see that's because of course even if in a large box you have a positive probability that all arrows are directing to the right side. Say. And then you see, of course, you can have for very exceptional omegas, you can have that you are exiting here, so with very large probability, or you are exiting here. But you see, this is because of this isotropic condition. So if you have a probability, if you have an exceptional omega with which you exit here with probability close to 1 to the right side, you have the same probability that you have omegas where you're exiting to the left side. This is just the isotropy assumption that we had on this mu. You should just always think on this example where I have this preferred arrow. So of course you have, okay, that has a very small probability, but you can have the situation where all arrows are directing to the right. And then even if the epsilon is small, you nevertheless have essentially probability 1 going out here. But you have the same probability that all the arrows are directing to the left, so, or directing up or directing down. So.
Okay, thank you.
Okay, I'm looking at this what people call quenched expectation here, and I'm writing it down as this perturbation expansion here. So now first I'm just looking at the term which is coming from this first order perturbation here, where you remember where I just once replaced compared this transition probabilities with the symmetric one here. So, and if you then compute, okay, this is also a vector here. So in the two-dimensional case, it would be a two-dimensional vector, and okay, you can compute the covariance matrix, but from the isotropic condition, you always have that this multiple of the identity, and the computation is just giving that. So that's it. So there's no doubt about it. So that's an exact equality here. So you're just having. For this first term, you're having just L minus 2. It's just because I have 1 divided by L here, and then just this what people call the bubble diagram. So this is just the Green's function square summed over the box, over the sphere. Yeah. And yeah, now okay, you see what is happening. Okay, that you can analyze in all dimensions. Okay, by straightforward computation. Here, so in dimension 1, the Green's function is of order L. So if you are in an interval, so you're okay, not at the boundary, but somewhere in the bulk, you are hitting on average a point L times. so before you are exiting, and then if you square it, you're getting L squared, and you sum it, you get L to the power 3, and you divide by L squared, you have it of order L. So this is, you see here the epsilon square is multiplied by L. So this means in dimension 1, okay, that's actually the situation. In dimension 1 here, the disorder on large scale is exploding. So you're just already in first order. So you're just multiplying it with L. Now the two-dimensional case, okay, it's a little bit more careful computation. You have to do the Green's function at the point 0 is log L, but if you are not at 0, okay, you have to be careful at the boundary, of course, but that is okay. That is well known. You just look in the book of Greg Lawler how this is going. So the Green's function, how the Green's function is behaving, and then if you do the computation, you are getting that if L gets large, you are just multiplying this parameter epsilon squared by 2 divided by pi. So you're just multiplying with it doesn't go to 0 and it doesn't go to infinity if L gets large. But you should be okay. Take into consideration that this is just all this computation is just by doing the first order perturbation expansion here. So in fact, we believe, and that is what we want to prove, and actually I think we are very, very close of understanding it. It's actually it goes to 0 if you take the full expansion here. So, but you cannot see it on the first order expansion. Now in higher dimensions, actually you see okay, it's easy to compute it. So in higher dimensions, it's actually going to 0. So you see if L goes to infinity. So you just divide epsilon squared by L in dimension 3, and okay, there's up to starting with dimension 5, you have L to minus 2, so epsilon squared. So that's the situation. So that the first order, you see the covariance of the first order expansion. So if L gets large, if the first order perturbation, if L gets large, is contracting the disorder. So that's the situation here. So, but you see, of course, this is totally okay. At first sight, it's not clear that this helps you anything because you see this perturbation expansion is, of course, you're just restricting here. So you see this consideration on this page. You're just considering what is happening with the first order term in the perturbation expansion. Now it's totally evident that if L is getting large, the first order term in the perturbation is not the relevant one. So that's really the question. So this just gives some indications also how things should go on. Now, you see, okay, the computation, actually you can easily see that if you fix L, so L arbitrarily large, and let epsilon go to 0, then of course the first order term in the expansion, in the perturbation expansion is giving the correct answer. But that is not what you want to know. So you want to know fixed epsilon and L go to infinity. And then the first order term in the perturbation expansion is totally irrelevant. So it's not clear at first that this gives you the right type of answer here. Now, okay, the way out, of course, is that you are doing a multi-scaling. So that's that you are choosing okay, a sequence of scales. Okay, you have to appropriately choose them. And then you want to go from, okay, I give some more indications a little bit later. Then you're always going, if you're going from scale Lk to Lk plus 1, you want to use properties on the scale Lk to get properties on the scale Lk plus 1, and you hope that you can do that just maybe. Okay, that the part which is coming from the lower order perturbation terms are more or less giving the correct answers. So that's the way how to do it. So now you see in dimension 3, if you believe that this works, and actually that essentially if you are stepping always from scale Lk to Lk plus 1, and if you're choosing this sequence of scales appropriately. If you hope that the first order perturbation expansion gives essentially the correct answer, you would expect that say epsilon square Lk plus 1 is just a constant times Lk divided by Lk plus 1, say in dimension 3. So because before in dimension 5 you would have a square here, but okay, it doesn't matter here. So. Now, for instance, if you take Lk plus 1 divided by Lk's constant, you should get an exponential decay in K, and which means because the Lk is of course exponentially increasing with K in this case, you would expect that you would get a polynomial decay of the epsilon depending on the scale L. But that actually has not been shown, so nobody has been able to show that. So all the results we have give a much slower decay. Yes, so.
When you have a central limit type theorem that doesn't say anything about this question?
Actually, the exit distributions are somehow simpler than the central. You see, the exit distribution essentially give a CLT up to time scale. So if you know that the exit distributions are essentially just the exit distribution of Brownian motion, then you know that the walk is essentially Brownian motion up to time scale. But to construct this time scale is actually a delicate problem. Yeah, so. You see, the Brickman-Coupian paper, which gives the CLT, is extremely complicated, and it's actually it's extremely difficult to read. So the paper I have with Oversight Uni is actually conceptually much more simple. But we just look at these exit distributions. So.
Okay, I just thought somehow just even talking about that work, it doesn't imply anything about these questions on this.
Yeah, I think you could milk it out probably. Yes, that's true. But we have tried to go to the other direction. So namely, first look at the exit. Actually, to look at this exit distribution has actually the advantage that if you have different boxes, then you are independent. So I wouldn't know how to. Okay.
But do you have Harnack type estimation? You initial point here is 0, but assume that initial points are distant less than L half, L over 2.
Yeah.
Then exit probabilities must be comparable.
Yeah.
Do you have such estimation or not?
Yeah, we haven't looked at it, no. So we haven't looked at that. Yeah, anyway, that's the result we have. So this is okay. I want mainly to talk about the two-dimensional case. So that is Erich Bauer. We actually dropped this isotropic condition to some extent. And actually, these are the first results without isotropic condition here. So namely, what we look at is at these exit distributions, and we compare it with exit distributions from ordinary random walk, and then you have to smear it a little bit. So because you see, if you're looking at these exit distributions very close to the boundary, you feel, of course, the random environment which is close to the boundary. So you cannot expect, say, that the difference of the exit distributions go to 0 in total variation. That you cannot expect. But with an arbitrary smoothing, I'm not very precise here but how we smooth, but with an arbitrary small smoothing, you finally can prove that in total variation it goes to 0. So essentially, the difference of the exit distributions after doing a little bit of smoothing is going in total variation to 0. So that's the result, and with Erich Bauer, we dropped this isotropic condition to some extent, which is actually in that case actually you have to modify that. I'm a little bit careless here. So this result in this sense is a result with Saituni, and then with Erich Bauer we dropped this isotropic condition, but then you have to modify that here. Because then you have to take the exit distributions of a random walk with adapted transition probabilities. Because you are not getting, if you are dropping the isotropic condition, you cannot get a comparison with ordinary random walks. So that was the main difficulty. So in this sense, maybe I should, for this statement, I should include here point 3. Now, as I already remarked, the K recursion we used is that we just, we went from scale Lk to Lk plus 1. So say the big box is here, the big ball has radius Lk plus 1. So then we just looked at exit distribution from the smaller scale, and then, if we exit that, we are starting drawing a new ball at the point where it exists, and goes on like that here. So, of course, you are getting a bit problems near the boundary, because at the boundary, close to the boundary, you have to scale down these balls to really catch the exit distribution from the bigger ball. Yeah, so that was the basic induction step we did in this three-dimensional case here. So we represented the exit distribution from the larger box through the exit distribution from the smaller box. And then, of course, you have to adapt the perturbation expansion, etc. But okay, that's of course a trivial point here. So. Now about the two-dimensional case. So as remarked, okay, that's some work in progress. So okay, we are working since a couple of years actually, and every year we are making a little bit progress. The first step of the iteration is just okay. The first step, okay, this is the quantity we have looked at before. So this is psi L. You should remember psi L were the expected, the quenched expectations of the exit distributions. So remember that. Okay, we had this exit distribution from large ball, and we compute the okay, that's a vector. So we compute the expectation of that, expectation vector of that. So in two dimensions, it's just a two-dimensional vector here. And we looked at the at this expansion. So from the first order, second order, third order, etc. So the first order is just that here. So you're just you have 1 divided by L, because we scale everything down with the factor 1 divided by L, and then we just have the Green's function. That's the Green's function of ordinary random walk here, and we multiply it with psi x. It's just, okay, that's just a simple computation you do. So you get that. So this is just this object, and then for the second order you are you have a slight difficulty. So you have 1 divided by L, and then you're having first the Green's function. And then we have this delta here. You remember delta x plus y was the difference of the transition probabilities of the random walk in random environment with the symmetric one. So that was just the difference. And then here, in principle, you would have also GL here. But as remarked before, we can always subtract here. Here we can take the discrete derivative here. So we can, in principle, you would have here GL at x plus e y. But you can always subtract GL x y because the summation over e of this delta is always 0. So you gain this discrete derivative, and then you go with psi, and then the third order is that here. So you get g and then delta, and then the derivative of g delta, the derivative of g psi, and you would go in this way. So these are exact computations here, so there's no problem about that. Now, the first observation is one as this puzzled us for quite some time. You remember, so in the that was a computation I did here. So if you look at that just as the first order expansion, you get the 2 divided by pi here. So now you have to realize that morally 2 divided by pi is 1. So now this is, of course, the 2 divided by pi is an artifact coming from the fact that in the first step you have independence here. But in the recursion later, you have to take into account. You see, later we are just looking at. I lost somehow. You see, later we are looking at things like that. So we are jumping from here to here, and then from here to here. And you no longer have independence because these balls are overlapping here. So if you are taking this overlapping into account, then actually the 2 divided by pi becomes 1. So that is a point which puzzled us quite for some time. So that so I'm just saying that morally you have to replace 2 divided by pi by 1. So that's okay. That's a little bit of a vague statement. So okay. As I remarked here, in later iterations, the ball to intersect become dependent here. So now actually you solve that by not looking at the variance. So or just at the variance or the covariances of this quenched exit, of this quenched expectation of the exit distributions, but you're summing over the starting points. You're looking at different starting points, and you're summing it, and you're just taking the sum of the covariances of that here. So, and then what you should consider is then L2 minus 1, and you are summing L2 minus 2, and you are summing over these covariances here of these things. You are averaging here. In that way, you are taking into account this later overlaps here. So, no, but okay, this just adds a relatively unimportant additional complications. And in order not to look at that, I just look at these variances here. So, just for instance, the variance of the first. You see, I had said the covariance matrix of this object here of psi L0 is a multiple of the identity, and therefore I can just look at the first component here, which and this gives the same as the second component. So I'm just looking at that, but I just replaced 2 divided by pi by 1. That's an unimportant, but a little bit disturbing issue. So you just say 2 divided by pi is 1, and then I'm looking at the variance. So instead of this more complicated object here. So that's an unimportant issue here. So now the proposition we have is that for any L, okay, it's still, you see, for any L, if epsilon is small enough, you know that epsilon L square is smaller or equal to epsilon square minus a positive constant. Actually, the positive constant is essentially explicit, times epsilon to the power 4 times log L in dimension 2. So with an explicit positive constant here. So that's the point here. And the final aim would be to look at the sequence of scales, so L1, L2, etc. Okay, chosen appropriately, and then prove that if you are jumping, going from scale Ln to Ln plus 1, you are getting the same inequalities here. So actually, okay, we have made some progress of proving that. So that epsilon square at Ln plus 1 is smaller or equal to epsilon square minus a constant times epsilon 4 times this log Ln divided by L. Now what we finally do is that we choose the epsilon, we choose the scales in such a way that the quotient is exactly given by the inverse of the epsilon at scale Ln. So that's just a technical tricky point to choose the scales appropriately. But this choice of the scales is just coming from technical considerations, which I cannot explain here, so which would take too long. Why we do it in this way? I cannot explain why we take it in this way here. So, but this comes up from a lot of technical considerations. Okay, which were going on like that. Then we would get that here. So, and that would of course imply that epsilon goes to 0. So, you see, in contrast to what is happening with first order perturbation, if you take into account higher order perturbation expansion, we would get this inequality, which would prove that epsilon goes to 0. So that the disorder is contracting to 0. And actually, it comes out here. This inequality, I will explain it a little bit. This inequality will come out by doing the perturbation expansion up to third order. So, if you would go on, if you do the perturbation expansion only up to second order, you are getting actually a plus sign here. So this is if you see you do first order expansion, then you do the second order expansion, then you see that you're getting a plus sign. Now you see that then you think things are going wrong. They are not contracting, which actually would be more interesting even. But actually, if you go up to third order, you see that you're getting a minus here. So that's a little bit of a tricky point here.
Oh yeah, that is very peculiar. Usually, wouldn't you expect that the being lower order, the second order term would dominate over the third order?
No, it's actually the cross term between third order. You have to go to third order to see the minus. Yeah. I think it's puzzling. So actually, I don't really understand. Maybe experts here in works in critical dimension can tell me. So you see, at first we thought actually it goes in the wrong direction because we just did computation up to second order. But then we realized actually that the third order plays a role because the cross term between third order and first order is making it contracting. Yeah, it's really a puzzling phenomenon. I don't understand the deep reason why this order should contract. But I think there are models where at the critical dimension it goes in the wrong direction. I talked a little bit a couple of weeks ago with Fröhlich. So he said, yeah, there are examples where actually at the critical dimension it goes in the wrong direction. So it's not. Now you see that it goes in the wrong direction if you are going up to second order. You just see from this variance computation. Actually, it's easy to see that actually if you look at the first order and the second order perturbation expansion, that they are uncorrelated. So the covariances are between the first order and the second order are 0. So if you look at the variance of this object here of first order plus second order, it just gives the variance, the sum of the variance. So, and you see the variance of that is not, is just essentially, okay, 2 divided by pi, but morally 1. So the variance of that is the same, that doesn't change the epsilon. It's just of order epsilon square. And you see that this should, okay, in principle be in principle of order epsilon to the power 4, but it would come with a positive, and actually it comes with a positive sign. So if you're taking just these two into account, you're just getting this expression with a plus sign here. So. Now, yeah, okay, I can again ask how much time I have, probably 10 minutes. No, 10 minutes, I guess. So that I should stop. I wanted to explain that a little bit, so because there are actually some quite interesting diagrammic expressions are coming in. So maybe I just explain it a little bit. Okay, quickly here. So if you're looking at the second order expansion, you are just okay. That was this expression, and then okay, because you are on the lattice, you are always having a little bit problems. I'm looking at the discrete derivative. And that I write as an inner product of the vector E. So vector E has length 1. So with a kind of gradient here. So I just linearize it, and then you have a rest term here. So okay, you have an error terms here. Now this gives a contribution of epsilon 4. Now you see what we are getting. The thing is technically quite complicated, but fortunately, what is fortunately happening that terms with epsilon 4 log 1 divided by epsilon are just rare. So most of the error terms are of order epsilon 4. So, but because we have terms with order epsilon 4 1 divided by epsilon log 1 divided by epsilon, we just can't forget about the epsilon 4 terms. So we are getting 2,000 of error terms of order epsilon 4. But these we can neglect. So this error, fortunately. So if you do this linearization, you're catching an error of epsilon 4, and then okay, this just means the first component because I just have to look at the first component. So you're just getting this expression here, and then if you do this, if you compute this variance, you're just getting this expression here. So you're just getting 0x1, 0x2. And then there comes the expectation, and here you have this gradient. Now that's a gradient with respect to the first variable here. So you're just having that. So you're summing over x1, y1, x2, y2. Now the point, okay, I just want to write it a little bit in the diagrammatic way. So you see we have expressions. Okay, you're going from 0 to x1. And here I have the gradient here. So from 0, you have to propagate the given by the gradient. And then from x1, you're going to x2. This is the derivative of the gradient. Now, the derivative is with respect to the first variable here. Now, this has a direction because you see g is, of course, symmetric. But the gradient is not symmetric here. So for that reason, I plug an arrow here. So just meaning from, you see, if you change x and y, the gradient is not the same. Actually, essentially, it just changes sign, but not exactly so. And then, okay, I'm having from 0 to y1. Okay, there's no error here. So, and then with an arrow to y2. Now you see this expectation is of course 0 if one of the variables xy, y1, x2, y2 is isolated, because then you have expectation 0. So the only way not to get expectation 0 is if you're having matchings between these variables here. Now, of course, you can have matching where x1 is equal to x2, y1 is equal to y2. Now, these matchings are giving, okay, you do the computation, this gives epsilon to the power 4. So we don't care about it because it don't have the log. So now what you can do is you're matching, okay, I have it on the next slide. You can do the matchings where you have x1 equal to x2 and y is with difference between y1 and y2. So in that case, you would get a diagram like that. You're getting that, and then that. You see, you just match that with that and that with that. Now you can also match that with that and that with that. Now in that case, you would get, so that's the case x1 equals x2 different from y1 equals y2. But you can also have x1 equals y2, which is different from x2 equals y1. Now this gives evidently a diagram of this type. And then you have to sum over the x and y's, x1 and xy1. So now this, okay, I don't have time to explain it in detail. But this part is just giving twice epsilon to the power 4 L square and then sum over x, y, and then the gradient. Now that's the gradient first in the first component, but then also the first component of this gradient here. So it's a little bit bad notation. The gradient is always on the first variable, and I'm just taking the first component of it. So it just gives that here. Now, if you argue in exactly the same way here for the matching of x, y with 1, 2, x2 with y1, you are getting, okay, this expression here which corresponds to this diagram here. And what you finally get is then you're getting for the variance of that, you are getting, okay, this, and then you're having this g. Yeah, okay. Now I have to add something. You see, in principle, I want to compare this diagram with this diagram. But what you can do is to move this leg to that. So I'm just looking. You see, this goes from 0, say, to x1, and here you would have then x2. So you have g0x1, g0x2, and then, okay, correspondingly here the derivatives of the Green's function here, which are reflecting this diagram here. Now I just want to replace the Green's function from 0 to x2 with the Green's function from 0 to x1. Now this causes, of course, an error. But the error is of order epsilon to the power 4. You do the computation here. So you finally end up with that here. So you're just getting twice that square plus, okay, where you here have gxy and gyx plus something of order epsilon 4. And now what turns out is that essentially these are antisymmetric. That's also not quite correct. But up to an error of order epsilon 4, you can just see that this is negative of that here. So you just cancel 2 here. So what you finally get is that this, so you're getting that here. So the variance of this object is here this, and then here you are getting essentially, you get the derivative of the Green's function against square. Now that you can easily compute. So at that stage you can easily compute because what you are getting is then you're just getting epsilon 4 to the log n essentially. So this is just a constant times log n. Yeah. So for large n. So that's then a simple computation here. So what you get is that the variance of that here is that here. So you see this goes in the wrong direction, except that we have not yet taken into account the third order perturbation expansion. Now the cross term between the second and the third order is again essentially 0. And if you're looking at the variance, that's epsilon to the power 6. We don't care about epsilon to the power 6 here. But what you have to take into account is the correlations between the first order and the third order. Now, and that is just also you can do it diagrammatically. Just let me explain that. So the first order you just have that, and then for the third order you have that, and you take the cross term. You can look at identifying this point with this point and this point with this point, but that you can easily see that this is of order epsilon 4. Or you can identify this point with this point and this point with this point. This gives also epsilon to the power 4. So the only interesting case is if you match that with that and that with that. So, and then you get again the diagram we had before. We just get this diagram. Now, as before, this is negative. So you see this is negative. And then, but fortunately, you see it comes twice. So because you see a plus b square is a square plus 2ab. So just by the binomial formula. So it comes twice. And therefore you're getting a minus here. So it comes with the same constant. Okay, that's our. Okay, of course, what we want to do is to do it for in the higher scales, and actually we have made a lot of progress to proving that, but there are still many details left to prove that from scale Lk to Lk plus 1. We have quite some understanding how to go on, but there are still many technical problems to solve. So it's not, we don't have the final results. I'm sorry that this is the situation at this moment here. So. Okay, thank you very much.
Even if you will complete this perturbation in any order,
yeah,
then you will prove homogenization theorem.
Yeah.
Only for Dirichlet problem. That in the Dirichlet problem, we have convergence. But to do this for parabolic problem, we need also control exit time. Tau L. Is it proven already? Tau L has order expectation. Tau L has order.
No. This is, of course, you are hinting at that. Okay, we are cheating here. So of course, because of this exit, you see, I don't really. Okay, I've also talked with Brickman and Kupian about it, what is really expected. So you see, here in that case, you just see that the exit distributions would be close to just Brownian motion. And you're right, okay, the crucial thing would be to control the exit times. And in the exit times, you could in principle get logarithmic corrections. And that we haven't seen it in the physics literature if there's a prediction about that. So.
But in the dynamic case, there are a lot of local cracks. And the motion will be slower.
Sure.
And L squared times logarithm or something like this.
No, exactly. That is, you see, but this is okay. People consider okay. I've also chatted with Brickman, Kupian. So these two-dimensional cases, really to prove a diffusive behavior and to have the proper logarithmic corrections, that's probably absolutely horrible, difficult. So So this is, we consider that to be as a first step, and I think it's quite nice that you can, okay, if you finally manage to do it, so that you can prove that on large scale disorder is disappearing without taking into considerations these possible logarithmic corrections of the which is needed for the diffusion scale. No.
Other question?
So from the very beginning you have chosen, like in your model, 1/4, right?
Yeah.
With probability 1/4, one of the four directions, plus epsilon there, minus epsilon third, and the others. Surely that's not only a possibility, right? The different models.
Entropy requires with rotations.
For example, you could have chosen quarter plus epsilon up, quarter minus epsilon down, and you choose with that would be a different analysis and different answers, right?
No, that would be the same answer. So that would be the same answer. Sorry. That would be a different answer. You're right. But that's a kind of model that I have investigated with Erich Bauer in the three-dimensional case, which is not invariant under rotations. But that we can do. I wouldn't expect any substantial difficulties here. But what you see, if you are dropping these conditions that you are invariant under rotations, you have the problem that you don't know from the start with what to compare. So you see, because actually what we proved with Erich Bauer in the case where you drop this rotational symmetry, we proved actually that you have a sequence of covariance matrix which you have just to construct step by step, so in a perturbative or in a multi-scale way. So you can never hope that you get explicitly the covariance matrix here. So it's just in the process of multi-scaling you can prove that actually you are having covariance matrices which have to adapt it from scale to scale, but which are finally converging. Yeah, that would be. We haven't looked at that. Okay, it's already in the two-dimensional case. This is already very complicated, so we didn't take that into account. That's just an additional complications, but not the principal problem. So to look at that.
In what dimension have you done that? With Eric?
Three or more.
Any other questions? Okay, let's thank both speakers for the